All right, so this is section 6.6. It is the last lecture for the course. Yay! But this is exponential and logarithmic equations. So the first thing we're going to talk about is utilizing like bases to solve exponential equations. And so in order to do that, we're going to use that one-to-one property that we discussed in the previous section. To where basically if your bases are the same, then really all that we have to be concerned about are these exponents. So if you'll notice here in example number 1, we have a common base of 2. So we can actually just take the exponents and set them equal to each other. And that is great because that makes this really, really simple. So here just solving for x, we'll end up with x is equal to 3, and we're all done. Love that. So if you want to give this one a try, if you want to pause the video and give it a shot, you should obtain x equals -2. So sometimes we're not given the same base, but we are capable of rewriting the bases so that they are the same. So notice here our bases are 8 and 16, and we should also know that we can rewrite 8 as a power of 2. And we can also rewrite 16 as a power of 2. So we can rewrite these with common bases. And so 8 becomes 2 to the third power. And then that's to the x plus 2 power equals. And then 16 becomes 2 to the fourth power, which is raised to the x plus 1 power. And recall the laws of exponents where if we have a power raised to a power, we just multiply those powers together. So this becomes 2 to the 3 times x plus 2 equals 2 to the 4 times x plus 1. And again, since we do have like bases at this time, we can just set those exponents equal and solve. And so we'll do that here. This would be 3x plus 6 if we distribute 4x plus 4. And then this will just be x equals 2. Right, and again, all done. So that is rewriting with a common base. So we could solve by setting the exponents equal. If you want to pause the video and try number 2, you'll obtain that x is equal to -1. Example number 3 is something similar. We want to rewrite a root with a fractional or a rational exponent so that we do have a common base. This will be 2 to the 5x, and as we know, a square root can be rewritten as a fractional exponent of 1/2. Bases are the same, so we can go ahead and set the exponents equal, and we'll divide both sides by 5 and obtain 1/10 as our value for x, and we're all done there. If you want to try number 3, you should obtain that x is equal to 1/2. Right, continuing on, solving an equation with positive and negative powers. We'll ignore that graph for just a moment. It's not part of the problem. It's just something I want to illustrate for you in a moment. So what we should notice here is that this is a positive base to a power, and it's saying that it's equal to a negative number. And so we should know immediately that there's no solution to this equation. And the reason behind that is because any power of a positive number is always going to be positive. And that's not the case here, right? We have that -2 on the other side. So there's no possible solution here. And if you're looking at the graph of this equation, notice that they've set the right side equal to y and graphed it. That's the -2. And then the 3 to the x plus 1 is here in blue. And because there are no intersections between the two graphs, there's no solution. And graphically, that's what that looks like. So if you want to give number 4 a try, you should also obtain that there is no solution for the exact same reasoning as above. Next section, we have solving exponential equations using logarithms. And so in this case, we're going to use some of the properties of logarithms and exponentials that we've seen previously in order to solve different problems. And so these have different bases. There's no hope of ever making these into the same base in any reasonable manner. And so what we're going to do here is we are going to take the ln, or the natural log, of both sides. And well, why does this matter? Well, the power property allows us to now move the exponent out into a coefficient or multiplied by the logarithm. And so we'll obtain this result. And then we just need to start cleaning this up. So the ln of 5 is a single number. And so we'll go ahead and expand by distributing that. And this will be x times the ln of 5 plus 2 times the ln of 5 equals x ln times the ln of 4. And so moving on, if we're solving for x, we should probably get all of the terms with an x on one side. And so I'll subtract x ln of 5 from both sides, and I'll obtain x times the ln of 4 minus x times the ln of 5. And then factoring out an x on the right-hand side, I'll be left with ln of 4 minus ln of 5. And then if we want to solve for x here, we're essentially just getting x by itself. So we can divide by this entire quantity because it is in fact just a number. So this will be 2 ln of 5 over ln of 4 minus ln of 5. And now that x is isolated, this is our answer. And most of the time, because these can be written in so many different formats, I will ask you to put that in your calculator and just round that to the nearest maybe 3 decimal places, and you'll obtain that that's approximately, change this to approximately, sorry, when we're rounding. So that's approximately negative 14.425. And now we're all done. One is just the exact answer and one is the approximated answer. So if you want to try number 5, try that same trick by taking the natural log of both sides. And ultimately, you should obtain an approximated value of negative 2.710. Darn it, I keep forgetting to make those squiggly equal signs to show that that is the approximate value, not the exact. All right, so now equations containing E. Remember, E is Euler's number, which is a constant like pi. And we've seen it again and again and again. So especially when we're working with base E, we really want to use the natural logarithm because that's going to have a base E. And it's going to make things really, really easy. So the first thing you want to do when you're given an equation that looks like this one is we want to isolate the exponential, right? So the e to the 2t. So we're going to divide both sides by 20 and we'll obtain 5 equals e to the 2t power. And so now we can just take the ln of both sides. So the ln of 5 equals the ln of e to the 2t. But recall that the ln of e, this is just the log base e of e, and that does in effect kind of cancel out, and we're just left with the exponent 2t. And then dividing both sides by 2, I'll obtain a value for t. So this is the exact value. And placing that in your calculator, you'll obtain the approximated value of 0.805, which, like I said, here will be more of what I'm looking for when you're taking any sort of test or anything like that. And so there is the answer for t. If you want to try number 6, you should obtain that t is approximately 2.599. So now example 7, solving an equation that can be simplified to the form that we just saw. The main idea is isolating the 2x. And so what we're going to do first is just the normal rules of algebra. We're going to subtract 5 from both sides. And then we're going to divide both sides by 4. Then once the exponential has been isolated, we will take the natural log of both sides and obtain 2x equals ln of 7 over 4. And then dividing by 2, we have x is equal to ln of 7 over 4 divided by 2, which is approximately 0.280. Okay, so if you want to try number 7, you should obtain that t is approximately negative 0.347. Right, moving on. So in some cases, we have an issue when taking the log or ln of both sides of an equation where we're left with extraneous solutions. And an extraneous solution, if we look right here, is a solution that is correct algebraically but does not satisfy the conditions of the original equation. And one such example is when we have the log of a negative number. And we saw a couple of lessons ago that can't happen. So this particular equation, there's a lot going on here. So just stand by and watch me do it. And then I'll kind of explain back through. So the first thing I want to do is I want to recognize that this is a quadratic because of that square there. Let's see. Sorry about that. This will be minus e to the x. And then let's move everything to one side equals 0. And so I know this is a quadratic because I can rewrite this using the power rules to look like this, so that in short, I really have this quadratic form where the e to the x is just kind of like the x term, right? So I have this thing squared minus this thing to the first power minus a constant, which is a quadratic form. And so in my mind, to solve this, I can think the following. I can think x squared minus x minus 56 equals 0. And what I'm going to be able to do here is factor this. And so this would factor into x minus 8, x plus 7, x minus 8, x plus 7, except remember the so-called x's that I have here are actually e to the x's. And so let's make that replacement now. So this would be e to the x minus 8, e to the x plus 7 equals 0. And I can set each factor equal to 0 and solve. So this is e to the x minus 8 equals 0. And e to the x plus 7 equals 0. And then I'm going to have two equations to solve, which makes sense because this is a quadratic. We should have a couple of solutions. This would be e to the x equals 8. And e to the x equals negative 7. And remember, at this stage, we're going to take the ln of both sides. So the ln of e to the x equals the ln of 8. And that's going to be x equals the ln of 8. And that's a valid solution. And then here, if we take the ln of both sides, we'll have ln of e to the x, which is fine, and ln of negative 7, which is definitely not fine, right? Because negative numbers are not in the domain of the logarithm. And so we call this an extraneous solution. And we don't consider it part of our solution set. The only thing we consider here is this ln of 8, which is approximately, let me see, ln of 8 would be about 2.079. 2.079. And so this is actually my only solution. So if you want to try number 8, you'll see that x should be equal to the ln of 2, which should be approximately equal to 0.693. Right, you'll use the same method of factoring there, get everything on one side, and then factor. So now using algebra to solve a logarithmic equation. So again, my primary goal, as it's been so far, is to isolate either the log or the exponential. And so the first thing to make that happen is going to be to subtract 3 from both sides, and I'll obtain 2 times ln of x equals 4. Dividing by 2, I'll obtain ln of x equals 2. And then I can actually, since I have the natural logarithm, I can raise everything up as a power of e using the definition of the natural logarithm. And I know that e and the ln in effect, not really, but basically cancel each other out. So I'll have x equals e squared. And I'm actually done there. So e squared is approximately, remember you can use your e button on your calculator, 7.389. So x is about 7.389. All right. If you want to try number 9, you should obtain x equals exactly e to the 4th, which approximately is going to give us 54.598. Moving on to example 10. So again, using algebra, again, then the definition of the natural logarithm. So again, our goal is going to be the same. We're going to isolate the natural logarithm. And so that'll give me 7 over 2, dividing by 2 on both sides. And then we'll raise everything up as a power of e. And on the left, we'll obtain 6x equals e to the 7 over 2. And then dividing by 6, we'll obtain e to the 7 over 2 power divided by 6, which is approximately, I don't know, let's see, haven't calculated that yet. So use my e button on the calculator along with the fraction button, 7 over 2. And then divide the result by 6. I should have 5.519 as my approximated value. 5.519. All right, so if you want to give this a try in number 10, I encourage you to do that. And you should obtain x is equal to exactly, x is equal to exactly e to the 5th minus 1, which is approximately 147.413. Moving on to example number 11. Again, disregard the graph until the end. It's just a visual to help us understand what that looks like. So solving ln of x equals 3, we should raise both sides as a power of e. And then we'll obtain that x is equal to e to the 3. And so here, we'll see e to the 3 is approximately 20.0855. And you'll see that in contrast to the earlier equation that had no solution, when we graph both sides of the equal sign, we do obtain this intersection, which is in effect our solution. So our solution is x equals this value. All right. If you want to give it a try for number 11, you should obtain that x is approximately equal to 9.97. Then moving on to using the one-to-one property of logarithms, which we've already seen. This just says that if the bases are the same for the logarithm, then we can set the arguments equal. And so remember that the argument is just what's inside the logarithm. So because the natural log has the same base, we can just set those arguments equal and then solve. This is quadratic, so I will have to solve this by factoring and moving everything to one side. And from there, I should obtain the factorization x minus 3, x plus 1 equals 0. Setting each factor equal to 0, I have x equals 3 and x equals negative 1. And so each of these are part of the solution set. So if you want to try the sample problem number 12, you should obtain x equals 1 or x equals negative 1. So both of those solutions are valid. Moving on, solving some applied problems using exponential and logarithmic functions. These are your favorite, the word problems. So here in this table, we have the half-life for certain radioactive, isotopes or materials and their usages. And here we have the half-life equation. And so let's talk about what each of these things represents. So this is called A naught or A sub 0. This is the initial amount. We know what E is. ln of 0.5, that's pretty standard. It's just a number. And so T is the half-life. Little t is the elapsed time. And A of t is the amount present after the elapsed time. So this is basically the amount after t time. So all of that given, we can solve some problems, right? So how long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? So you'll notice here in your table that this is the half-life of uranium-235, which is really, really long. And so let's go ahead and kind of figure out what everything is. A of t is something, a naught is something, t is something, and little t is something. So these are the values that we need to identify. It says that there's 1,000 grams to start. We see that 703,800,000 years is the half-life. And we want to know how long it's going to take 10% of it to decay. And so the amount remaining with 10% being removed is going to be 900, right? So that means if 10% is removed, 90% remains. And so to calculate that, we'll just multiply by that percentage as a decimal, and we'll obtain that 900 should be left after 10% is removed. And so from there, really all there is left to do is to plug this into the formula. So this is going to be 1,000 E. And let's go back up and make sure we can see the formula. So this is going to be all in the exponent ln of 0.5 times t, which is what we're solving for. And the half-life is actually this god-awful number, 703,800,000. And so to solve this, remember before we wanted to isolate the exponential. And so 900 divided by 1,000 is going to give me 0.90 equals e to ln 0.5 of 703,800 million gazillion. Just kidding. And so then remember, to get everything out of this exponent, I need to take the ln of both sides. And so when I do that, I'll just be left with the exponent, which is all this, 703,800,000 times t. And then because the operation with the variable we're trying to solve for is multiplication, I can just divide by all of this, right? So in my calculator, I can just put a fraction in a fraction, and I'll just have divided by ln of a half divided by 703,800,000. And then that will give me my desired t value, which will be approximately 106,979,777 years. Wow, that is a super long time. Anyway, so that's the applications of some of these functions, in particular half-life. So if you want to try example number 13 and see how you do, make sure you go up there and grab the half-life of uranium-235. We're still working with that same substance. And you should obtain that T is approximately 226,572,993 years. And so that is the very last little bit of our lecture for this semester and for the course. So I hope this helped, and we'll work some problems on these particular topics on Wednesday.